Okay, hello everyone. Yeah, I'm Jana and I'm from Slovenia. So I'm a meteorologist working at the Slovenian Environment Agency. And like in the previous couple of years, I spent a little time looking at the IASI profiles, and yeah, I try to see what use we can get for our forecasters. My talk today is divided into two parts. So the first one will be really connected to the IASI profiles. There's a little bit of validation, a comparison with aircraft data, and then I'm going to look at the stability indices. And in the second part, I'm not going to use the satellite data, but well, I'll present a little study that has well, relevance for the satellite retrievals and for the calculation of stability indices from these satellite profiles. Okay, for the beginning, I have a little challenge. Okay, so I have a little challenge for you. This is well, temperature at one of the lowest levels of the IASI profiles on one certain day. Okay, and now here are a couple of profiles. You can, well, yeah, you can see they are connected to the certain points here in the map, and I want to ask you, which of these profiles would you think is the most unstable? So this here is not Cape or anything else; it's just the temperature, and I want to invite you all to just try to vote for the profile that is, well, where you think the environment is the most unstable. Yeah, just take your time and mark the one that's, well, okay. Any more guesses? We have 4 now. Okay. 6, 7. Well, if you want, maybe you can just write to the into the chat why, like some comments, why you think why you chose these two profiles. Anyways, yeah, thanks for your responses. I'm just going to continue because, well, I'll be a little bit short in time. Well, actually, this was quite a good guess. If we look at these two profiles, we do see like a little region with quite steep lapse rates. There's a region that has quite some moisture, and well, we have this profile here that is more moist, but the lapse rates are really low, and this one is drier. And when we actually calculate the Cape from this is the result. So you can actually see that these two profiles correspond to are from these points where we have the highest Cape values. Okay. Now I have to, well, here a couple of images from the same day for the whole Europe, and you can see that we have this this quite unstable area here, and what I'm showing you here are 3 different indices, and we have Showalter index, and the Cape, and the K index. Well, I'm going to, in this first part of the presentation, I'm going to focus more on the Showalter index and the K index. Well, the Showalter, because it's quite widely used by our forecasters here at ARSA. The K index because it's simple, and Cape, I will save Cape for later. Now I'm going to the data. In the continuation, I will focus on the comparison of the IASI profiles with the aircraft data. We were trying, when we started using IASI profiles, we wanted to compare them with something that we're familiar with, and our forecasters quite often look at the aircraft profiles well, just to get some more information, additional information to the radio soundings. So we decided to take aircraft profiles to compare these IASI profiles. Oh, first I'm going to show you what happened actually on the day that we have here in this region with huge cape and other index values. It was a day with several storms in the eastern Slovenia and Croatia, western Croatia region, several hailstorms, a lot of damage, and well, the largest hailstones were up to 12 centimeters big, and like damage was really bad. But it's nice to see that we could see several hours before in the IASI data that there was something going on. Okay, now let's go to the data. I'm using, for the comparison, I'm using the data that Thomas presented yesterday. So it's just the same thing that you saw yesterday. I'm not going to go into the details here. And then I compare this data to AMDAR measurements. So these are measurements from commercial aircraft flying like typical, well, that they fly the normal lines every day. There are 10 Lufthansa aircraft equipped with humidity sensors. There are many others equipped with temperature sensors, but we chose those with humidity just so that we can compare both values. You can see a couple of characteristics here. Anyway, I'm not going to go to the detail here. I'm going to show you the coverage of this data. It is one day in April. No, it's the whole April of 2017. I did the study for the whole year 2017, and you can see the tracks of the aircraft from which we have the profiles. So we don't have the data from when they reach their flight level. We just have the data when they start approaching the airport or when they ascend. Okay, so this is the coverage, and probably this year this image would look quite a bit different, but luckily in 2017 there was a lot of data to compare. Now we took the IASI profiles and we collocated them to the AMDAR profile that we had in the same time frame. Now we could do this comparison with radio songs or so, but like typically the radio songs are launched at 6 UTC or 12 UTC, and the overpass of IASI is somewhere between 8 and 9 in the morning. So it just, well, the time difference is quite big. That's why we decided to use the AMDAR profiles and chose the collocation criteria with the maximum distance of 50 kilometers and maximum time difference of 1 hour. And what we do here, you can see in gray, you can see one AMDAR flight, and in black, you can see the corresponding IASI profiles along this track. So we don't take one IASI profile and one AMDAR profile and match them because the distance is just really huge. But we take several IASI profiles along the AMDAR flight and match them then. And this looks like this. So this is just an example from the same day before. In black, you can see an AMDAR profile. This is the dew point temperature and this is temperature. And in red, you see the IASI profile. The blue lines just represent the differences between the two. And this plot shows you the collocated, the matched measurements. Okay, so we have 6 IASI profiles along one AMDAR flight, and they're represented here in different colors. And the size of the point represents the distance. Okay, so we see that we start a little bit further away from the nearest IASI profile, and then we approach it, and then again we go away with our underflight, and then we jump to the another IASI profile, approach it, and then go a little bit further and continue all the way to the uppermost level. Okay, so we construct our IASI profiles from different IASI profiles that are nearby, okay, that are along the AMDAR route. And we use these profiles to calculate average values for the whole year, okay? We simply take all the matching data and put them into this average vertical profiles, okay? So what I'm showing you here is the bias and the standard deviation of the, well, it's hard to say the bias because we just compare two different data sets which have their own errors and everything. But so it's just the difference between the two data sets. Okay, we see that compared to AMDAR, IASI is a little bit colder, and we have approximately like 1.5 Kelvin standard deviation. And here we have the dew point temperature, and we see that the variability is the largest, like in these mid levels. Okay, but there's not much difference in terms of bias between the two. We did that. We did a seasonal comparison of these profiles, and I'm showing you here the temperature. And what we can see is that this, well, the spread, the standard deviation here is quite similar in all seasons. A little bit larger in the winter, and we see that this click here in the winter with the kind of the largest difference between AMDAR and IASI, and this is due to inversion situation, temperature, when we have temperature inversion. And we learned yesterday that IASI profiles are much smoother than like typical in situ measurements. So we get this when in situations when we have this large gradients in inversion situations, we get these larger differences. Okay, and then also in the summer, the differences are the largest at the bottom. Okay, a similar thing here for the dew point temperature. So still, again, the largest differences are at the mid levels, and not so much at the lowest levels. We can also look at the specific humidity, and what we notice here is that this spread, the variability in this difference between AMDAR and IASI is really much larger in the summer than it is in other seasons. So in the winter, it's really low, but it's clear that the values of specific humidity are also much lower in the winter than they are in the summer. And in the summer, we also have more small-scale phenomena in the atmosphere, so the variability is larger, and the IASI profiles just it's more difficult to follow that variability. Okay, this I'm showing you this because this has implications for calculations of the stability indices that we for obtaining the stability information that we actually want to get from these profiles. My next slide is showing you a kind of similar information than as before. I'm showing you here temperature in red and specific humidity in blue, and there's like starting here at the bottom, this is the standard deviation, the variability between the two data sets at 500 hectopascals, and this is the bias, so the difference. And we can see that the IASI profile are a little bit colder. So maybe I should just explain that here I take all the measurements from one day, average them and calculate the standard deviation. And we have here the whole year of 2017, and each point represents like the mean bias from like 1 day. Okay, and well, we averaged over 2 days, so that there's not so much variability. But you can see now how this bias and standard deviation develop throughout the year. Okay, now we see that the temperature is always a little bit lower in IASI than in AMDAR, and the standard deviation is pretty much the same throughout the year. What we see here on the right is that the temperatures tend to be at 850 hectopascals. The temperatures tend to be quite significantly lower in IASI than they are in the AMDAR, but only in the winter. Okay, and well, the standard deviation maybe is a little bit bigger in the winter, but it's just a minor difference. Now, when we go to the specific humidity, we see that the bias at the 500 hectopascal is almost, well, there's almost no difference. And in the 800 hectopascals, the values from IASI are a little bit lower than those from the AMDAR. But what we notice is that the variability of these differences between the two is much higher in the summer. So we have August here and June here in the summer than it is in the winter. Okay, and it is the same at 500 and at 850 hectopascal. So these are the levels that are quite important for calculation of several instability indices that we are used from the radio soundings. Okay, if we continue, now I'm going to look at those stability indices. And I'm just going to take two, Showalter index and K index. And the reason why I'm not taking the CAPE or other indices is just simply that AMDAR profiles just don't reach high enough to be able to compare the CAPE with the IASI profiles. That's why we can compare only these two. And what we did is we calculated, from all the matching profiles that we had in the year, we calculated the Showalter index and the K index from AMDAR and from IASI, and we built a kind of a contingency table. So I'm not, well, this yes and no doesn't mean that actually something happened. It just says that in AMDAR there was a possibility of the Showalter index has values that show possibility for a storm to develop. And here we use the thresholds that are typically used in the literature for, well, the Showalter index lower than 0 could mean that something is going to happen, or K higher than 30. Okay, and we can see that the probability of detection with this threshold is quite low. Okay, so like 24% for the Showalter index and 32% for the K index. This doesn't look really well, but we tried to change the threshold. Okay, now those indices were developed for radio soundings. Okay, for in situ measurements. They're so much more. They show so much more variability, and our profiles are smoother. So we have to adjust something to be able to look at the same variable. Okay, so we tried with some new thresholds, like we took the Showalter index of 3, the threshold of 3, and K larger than 20, and now our probability of detection just jumped up. Okay, we still have a lot of false alarms. You can see it here, and the number is high, but it's still promising. So we can see that it gives us a possibility that if we adapt our thinking when looking at these stability indices, we can actually use them to get useful information. Okay, and I'm just going to sum up this part. So we've seen at the beginning that the IASI profiles can give us really relevant and useful information in cases of well, for when we have severe storms. Now, we've seen yesterday and today that these profiles are much smoother, and so they miss the variability that is present in the atmosphere. And we have to just, we just cannot use the same indices in the same way as we did it with the radio soundings, but we have to adapt our thinking or, the interpretation of those classical stability indices to use them for our forecast. Now I'm going to move to the other part. And here we have it. Now I'm going to use the case. And we had a question. If we know that we have errors in our retrieved profiles, how do they propagate to the calculated stability indices? And for that, we use the Monte Carlo method. So we take one profile, we perturb it randomly, and then calculate CAPE for many times. And then we build a distribution of those CAPEs to see how they behave. And I just want to acknowledge the help of Xavier Calvet and Niobe Peinado from Nowcasting staff. This work was done in cooperation with them. So I want to ask you, just shortly annotate here in your forecasting work, which CAPE do you use most often? I mean, I saw yesterday that there are some forecasters among you, some researchers, but probably all of you have been in contact with CAPE somehow. Okay. Okay. I have to stop. Okay, I'll go on. Okay, so obviously most of you use the most unstable CAPE or the surface-based CAPE. Just to the short to present the three different CAPEs, we can different CAPE calculation comes from the different air parcels that we choose to calculate the CAPE. So, okay, we need a rising parcel that starts either from the surface conditions, which is called surface-based parcel, and the CAPE calculated from this parcel, the surface-based CAPE. We can start the parcels from the mixed layer conditions, which is the average conditions of the mixed layer, which can also be very different at different centers. And the most unstable CAPE is simply the highest CAPE from different parcels in a layer of different depths. Okay. I'm going to take two cases to look at the CAPE, and I'm not going to go into the details here, but we took the Tenerife case of 2002, where there was a huge flooding in Santa Cruz de Tenerife, and then the Joplin case, there was an EF5 tornado near the town of Joplin, which caused huge damage and 158 fatalities. These are the cases, but I'm going to focus on these profiles. So this is the well, in green you have the dew point temperature, and in red you have the temperature, environment temperature for the Tenerife case and the Joplin case. Now the difference here is that when we calculate all these parcels and calculate CAPE, we see that these CAPE profiles are very different. We have about 600 joules per kilogram CAPE here, and we have around 4,000 joules per kilogram here. And it's just two very different profiles, but we're going to perturb these profiles to see how they behave when we do it. When we do Monte Carlo method, we have to apply random perturbations to our profiles. Now, we used the uncertainty covariance matrix from Nowcasting staff retrieval algorithm that shows us the uncertainty of temperature and dew point temperature at each level that we look at. Okay, this retrieval has 90 pressure levels, and we just selected an appropriate subset for each profile. Now, this, like the perturbations at each level are not independent, and this makes the whole thing a little bit complicated. So we have to diagonalize this uncertainty covariance matrix through the eigenvalue decomposition. So we calculated eigenvalues and eigenvectors and transform the matrix into the eigenspace where it is diagonal, and there we apply the perturbations and then we transform this back into the physical space, and this is an example of what kind of new profiles we get. Okay, in the dark green, there's the regional profile, and this light green presents the new profile, and here in the light red there's an old profile, and the dark red presents the new profiles. And we did this for 1,000 times for each kind of cape, and now I'm going to leave this. What we get is a histogram of capes. So what I'm showing here is a surface-based cape histogram for the Joplin case. What strikes us the first is that this histogram has really a huge spread. Okay, like the standard deviation here is 50% of the cape of the original cape value. Okay, so we can see that just with the perturbations with the amplitude that is like typical for satellite retrievals, we get huge spread in cape. Okay, so we can get much less cape and much more cape than we had like our original profile had. We did the same for the most unstable cape and the mixed layer cape. What we see is that most unstable cape is simply a little bit higher than the surface-based cape, and the mixed layer cape has a slightly less spread. Okay, because we take the average of the lowermost four levels, and this makes the spread simply a little bit smaller. However, when we now look at the Tenerife case, we see a completely different distribution, and we don't see the kind of Gauss distribution anymore. It's not even exponential. What we see here is that we have a large number of cases where we have zero cape. Okay, so when we have small values of cape, we don't just get a little bit less or a little bit more when we have this perturbation, but we have weights about zero cape or some cape. Okay, so we have a lot of cases where in such a case we simply don't get any cape. Okay, the information about the instability is lost here. Now, yesterday we heard that some people are trying to apply corrections to the retrieved profiles to reduce the error. And typically, the two corrections that you can apply are the bias correction or the surface correction, like the Hungarian colleagues are doing. We tried to simulate these two corrections in our study. So we just applied like 1 Kelvin correction at every level like in one case, and then the other correction was we took the perturbed profile and just reduced the lowermost level by 50%. Okay, so we wanted to see what happens if we apply these corrections. Now it's a comparison of the Joplin case, and here you have the normal histograms of the perturbed case, and this is the histogram with the correction, applied correction. It's a lot to see, but you can just see that capes in this case are a little bit lower, but for the surface-based cape and the most unstable cape, there's no difference, okay, in the spread. There's a little bit less spread for the mean layer cape, okay, but it's not much. When we go to the Tenerife case, there's here for the mixed layer cape we have much smaller spread, but again we just get lower values of cape. Now, when we apply the surface correction, what we see, the first thing that we see is when we calculate surface-based cape, obviously the spread reduces for about half. Okay, and this is also the same for the most unstable cape, because in the most cases the most unstable cape is the surface-based cape. But we don't see as much impact when we calculate the mean layer cape, the mixed layer cape. Okay, it's just because it's just one of the values that we take in calculation of the mixed layer cape. Well, that's why this correction simply doesn't have so much impact on the mixed layer cape. Again, we see for the Tenerife case, you can see that it has a lot of impact. Here, we don't have so many mixed cases. Okay, the distribution does get a peak about the regional cape value, and not so many zero cape values. Okay, but again, you see that for the surface-based and most unstable cape, and not really for the mixed layer cape. And I'm going to finish now with, we've seen that that the uncertainties in the retrieve profiles lead to really large uncertainties in cape values. Okay, and when we have small cape values, this leads to mixed cases. Okay. We saw that the uncertainty of mixed layer cape is slightly lower than of other capes, but on the other side, when we apply the corrections, those corrections have kind of like, at least the surface correction has the least impact on the mixed layer cape. So, well, this is it, and I'm happy to take any questions.